52 is more practice with volume. So some of you guys are coming to me or texting me and saying, hey, I'm having some issues with when it's around the line x equals -2, y equals 4, things like that. I never know if I should be doing dy or dx, and we're going to figure that out. So we're going to do some more examples today of those types of questions. So this first one says we have y equals 1/2 x cubed, and we have y equals 4 and x equals 0, and we're rotating around the line y equals 4. So if we have y equals 1/2 x cubed, that's like the x cubed graph, just kind of vertically compressed. We have y equals 4, and we have x equals 0. So what I would always do is I would shade the region that we're rotating. So we're going to lightly shade this little region here. Okay, so that's the region that we're going to flip around. So we're flipping it around the line y equals 4. So when we rotate it around this line y equals 4 really, really quickly, we create a shape. Okay, it's okay if you cannot draw the shape. Some of you guys admit that you are artistically challenged. I get it. So you can't draw it. That's totally fine. I know, Julia's like, I got the art stuff. I got this figured out. Can you at least visualize in your head what this looks like?
A bowl.
It looks kind of like a bowl. Do you guys agree? Like a little bowl? Maybe a little pointy on the bottom of the bowl. Looks like a bowl. It does not have a hole in it. It's not an open bowl, a solid bowl, right? Like that. Like a contact lens that's filled in. I don't know what it looks like. But it is totally filled in. It is solid. Okay, kind of like a hemisphere almost, only I think it's a little bit pointy at the bottom. It's not quite a hemisphere, but maybe a hemisphere. Do we see this?
How would you know?
You rotate around that line, so you get like something like that. But it's solid. Okay, do we have a hole cut out of it? Do we have an inner radius?
Yes.
We do not. The whole structure is solid. It is not a bundt cake. Do we know what a bundt cake looks like?
Something my grandma makes.
A bundt cake you could make for Pi Day. My calculus classes always seem to like making bundt cakes over the years. If you would like to make a bundt cake, you can do that. Because a bundt cake is something that we talk about in calculus. It's from this disc and washer. All right, so anyway, so we're going to set this up, and we're going to do our volume, and it's going to be the pi. Am I going around the x-axis or the y-axis? Or something that looks like the x-axis or y-axis? What does it look like, x or y? It looks like the x-axis, right? It's just kind of moved. So we're going to integrate with respect to x because we're using this disc and washer method. And our x values go from here to this intersection point. You can find the intersection point by setting 4 equal to 1/2 x cubed. We end up getting x equals 2. So that's 2, 4. So we go from 0 to 2. And then we need our radius. So in this case, we don't have an outer radius and an inner radius. We just have an outer radius. So when you draw your outer radius, you always go from your axis of rotation all the way to the outside of the curve. It is not 4. Mine looked kind of like 4 because I didn't draw it very well. But what if I started here? That's not 4, right? I could start anywhere between 0 and 4. It's 4 minus 1/2 x cubed. Okay, it's because we're asking for the distance between this line and this curve. So what is the top part of it? It's the line 4. What is the bottom part of it? It's 1/2 x cubed. Just like when we were talking about on an axis, if I have 8 to -3, that distance is 11. 8 minus a -3. Now it is not super important that you get this right now, that you understand the top minus bottom concept. However, do you guys see on the backboard how I have all these little manila folder things with the shapes, all the circular cross sections, the square cross sections, the triangles? We're going to be doing things like that soon, and it does matter if you don't do top minus bottom for your height there. So do we all understand that this height from our line y equals 4 down, that height of like a rectangle, if I was drawing a rectangle in, would be 4 minus the bottom curve, 1/2 x cubed. Why did I not write 2y under a cube root? Why didn't I not solve for x instead? Because it's going around something that looks like the x-axis, right? So our r is going to be 4 minus 1/2 x cubed. And if you do your setup and you just say pi r squared dx, you're good. You would get that setup. Okay, or you can plug in.
So how do you know if you need a big R and a little r or just big R?
If there is a hole cut out of it, then you will need both. So you guys can do this on your calculator. It was a weird number, 144 over 7 or something. I don't know, what was it? 144 over 7 pi? I don't know why I memorized crap like that. I've only seen this number one time.
I thought the pi went inside the
It can go inside the integral, or it's a number, so you can pull it to the outside as well. So pi, I typically will put in the front because I do my math 9 stuff without the pi, and then I put it in the end. All right, so that is our answer. All right, so the next one, 7 is kind of crazy. So the next one, so I have 6 minus 2x minus x squared. So we can graph that on our calculator if we want to find our intersection points, or you could do it all by hand. Do we at least know what the shape is? A parabola, yes, a parabola. AP calculus, guys. All right, a parabola. Yes, it's a parabola. I hope that was a joke. I know it probably was. Oh, man. I taught Algebra 1 first semester. They definitely called it parabolas. Okay, so we got this parabola, and then we have it intersected with a line, right? And we have these 2 intersection points. So you can find these 2 intersection points. Do you guys know what they are? Go ahead and find them for me. Yep. So Emerson's helping us out. He said it was -3, 3, and 0, 6. And that is the intersection point. So you can find those doing your second trace intersect. So our shaded region is right in here. That is the part that we're rotating around something. And in this case, we're rotating around the x-axis. So does this one have an outer radius and an inner radius, or just an outer radius? It has both, because we're going to go from the axis of rotation all the way to the outside of my shaded region. That's my outer radius. That's r. And if I talk about that distance, think about a rectangle. If I had that rectangle and I wanted the height of the rectangle, its height would be starting from the top curve, which is the 6 minus 2x minus x squared, minus the bottom one. Well, what's the bottom one? 0.
Why is it 0?
Because it's the x-axis. It's right here. So we're going from here to here. And then our inner radius,
X plus 6 minus 0.
it is x plus 6 minus 0. Or you could just say x plus 6. Good.
Wait, what?
Top. So our top curve was that, and our bottom curve was that.
Why isn't it 6 minus 2x minus x squared minus x plus 6?
Because we're not finding an area, we're finding a volume, right? So she's saying, why was it not 6 minus 2x minus x squared minus the other curve, x plus 6? We're not finding the area of this, we're finding the volume when we rotate it around. So in order to do that, we need an outer radius and an inner radius. We're creating these big, like, rings. So the washers. Yeah, Abby?
I get confused on like how to tell whether or not it's gonna have like a hole in it or if it's just gonna keep this.
Okay, when you're going from your axis of rotation, if your shape is already on that axis of rotation, do you guys see on this last one? That shape was up against this axis of rotation. There's no hole in it then, right? There's no inside part that we're subtracting out.
Yeah.
Okay, so nothing that we're scooping out is what I was saying, like as if you had clay and you had those tools where you're like scooping out extra clay. We're not doing that. Okay, so we do pi, and we do our outer radius, which was that 6 minus 2x minus x squared, and we're squaring it, minus the inner radius, which is x plus 6. So we have our pi r squared minus the other pi r squared. And we're going from, Emerson said this was -3, 3, so -3, and this point was 0, 6, so we're going from -3 to 0. We're using those x values because we have everything integrated with respect to x, because it's a horizontal axis, right? And then we can find that number. Did you guys find it? Yeah, you put dx. You don't get a bonus point for that, though, because if I got bonus points for all the times you guys left off a dx, I would have lots of bonus points. If I got a penny every time, I would have like $1 million by now from teaching AP Calc. Yes?
I have a question on the one before, actually.
Uh-huh.
So did you do 4 minus the 1/2 cube because the line that you were revolving around was the 4 4 and then minus the below curve.
Yep. So we were talking about the distance from this line to this line, right? 4, and then minus the other one, 1/2 x cubed.
So essentially, if that was revolving around 0, you would not have to worry about it.
If you were revolving around 0, you would get, so he's asking on this last example, what if we were revolved around this line instead?
Which you then have to do 4 squared.
You would have an outer radius and an inner radius on that one, because you would do outer here and inner. Yeah.
So if it were revolving around like a y-axis, would it be in terms of like right to left?
It would be.
Okay.
So if y-axis, you're doing right minus left, so your outer radius squared minus your inner radius squared, and those come from the right minus left distances. All right, so the same one, so it says we have the same curve here. So we have our -3, 3 is the intersection point, and then 0,6. 48.6 pi was the last one. So you could write that lots of different ways. Fractions, whatever you're using. What is 48.6 as a fraction? So 243 over 5 pi? No, 300? Yeah, 243 over 5 pi. All right, so this one's going around the line y equals 3. I was doing negative. So right here. So shade in that region that we have. In order to go from my axis of rotation to that region, do I have an outside length and an inside length? Yeah, I have 2 lengths, right? Do you guys see them? So we have all the way to the outside of the curve, and we have all the way to the inside of the curve. So our big R, if I go all the way to the outer part, are we still in terms of x? Let's wait. Are we in terms of x? Dx? Yeah, because we have a horizontal axis, so still dx. And it's going to be this top curve and the bottom, whoops, not bottom curve, bottom curve, right? That's that distance there. So our top curve is that 6 minus 2x minus x squared. What's the bottom curve this time? 0? 3, right? So minus 3. So the outer radius is 3 minus 2x minus x squared. And our inner radius is going to be x plus 6 minus 3. You got it. Okay, so as long as you set it up and you have volume equals pi, -3 to 0, and you do like big R squared minus little r squared, as long as you've written what those r's are, you're good. So in your calculator, what I'll do a lot of times, if I've already done that part A, where I had like, you know, that was originally like y1 or y2 or whatever, you can do like y1 minus 3 and y2 minus 3. Like you can do that on those, right? So you don't have to retype all of it. But. All right, did you get that one? You guys are faster than me, but -3 to 0. Oh man. 21.6 pi. So 108 over 5 pi. That is right. Good job. All right, are we getting it more? Okay, try a couple more. All right, so I have x times y equals 6, y equals 2, y equals 6, x equals 6. Around the line, x equals 6. This is a hard one to graph. Do you guys at least know what x times y equals 6 kind of looks like? What's its parent function? Not quite, almost. Yeah, it's like this. It's like 1 over x. It's just 6 over x is our function. So if you wanted a couple points that you were trying to figure out, like if you solved for y, let's say, you'd have 6 over x. So a couple points to help us would be like 1 comma 6. We could have 2 comma 3, 3 comma 2, 5, 6 comma 1, right? And then you can start to see that kind of hyperbola shape in there. Like that. So that might help if we draw it kind of precisely, because these are going to start to intersect it in lots of different ways. So we have y equals 6, y equals 2, and we have x equals 6. So do we see the region bounded? This little region right here. And we're going around the line x equals 6. So here's our axis of rotation.
What would that create?
It creates like a kind of like a dome with like the top of it kind of flattened. When we chop things off in math, we always call it truncated. So it'd be like a truncated dome. I don't know, like weird shape. Imagine making a birthday cake that's kind of rounded on the side. All right, so here we go. So let's see, this time we have x equals 6, which is a vertical line that we're rotating around. So what does that mean? Yeah, so we're going to integrate with respect to y. So when we set this up, we're going to have our pi, we're going to have our dy on the end, and we're going to go from y values. So because as we do our vertical cross sections, so we're getting circular cross sections. These are like little circles here. Those circles are changing height, like depending on where y is located. So that's why we integrate with respect to y. So it's saying for y equals 2, we have this circle. For y equals 2.1, we have this circle. For y equals 2.2, we have this circle. All right, so
And this one does not have a hole inside.
it does not have a hole inside, correct. So it just has an outer radius. So from our axis of rotation to the outside of the shape, we have an r value. Just like when we have a number line and we say, oh, we're at 10 and we're going to -3, we do 10 minus a -3 to get a total of 13. So what am I going to do for my outer radius? 6 minus 6 over x? 6 over y, right? Because we're going to solve this equation for x. So we get x equals 6 over y. So we're going to have 6 minus 6 over y squared. That's going to be our volume equation. Where are we doing what?
How do you know it goes from
How do I know it goes from what?
2 to 6? I get the 6.
It's from what y value to what y value. We start here and we go to here. So you're saying start at y equals 2 and we go all the way to y equals 6. What did you guys get? 17.4? Is that what you said? Did you guys get that? Okay. I didn't get it because I thought I was holding my old calculator, and I'm not. I'm holding this other calculator, and I did like Math 9, like the F and int in my head, and I did the comma, x, comma, blah, 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 and then I realized it had set up as an integral. It was like syntax error, and I was like, what did I do? Oh, wait. Maybe I should look. All right, so what do we get? 40 over 3 pi. Anybody second that? 40 over 3? All right. Sorry, YouTube viewers, if they're wrong. They're telling me it's 40 over 3, but don't write angry comments on my page if it's not. It's Friday, and they're tired, and they're doing the calculating for me. No, I only get nice comments.
Having a nice voice.
Yes.
Do people say that?
What was it? 70 what?
76.
That's what Grant said.
What fraction is that? Give me a fraction here.
There's no fraction.
It doesn't.
When you
Ooh, I don't
subtract-
like this.
You multiply it by pi, you get 241.58.
I'm verifying because it bothers me. It doesn't come to a fraction, huh? So I'm guessing there's some kind of, it's having trouble with its bits and bytes here, huh? We'll do 76.9, and I'm going to do 900 because I've rounded, right? And I want the AP test to know that I've rounded. It was 76.89999. But sometimes when I have that anyway, I just multiply by pi, and I would write like 241.588 instead. Because if you're going to have a decimal with pi, you might as well just multiply the pi in, right? All right, are we feeling better about this? Can we stop now, or you need to see more?
Now, but I don't feel great about area.
Now it's like, oh man, I forgot all of the area stuff. All right, we'll stop there.